The cosmos is hiding profound secrets in plain sight. Data from our most powerful telescopes and probes contains anomalies that defy all explanation, challenging the very foundations of modern astronomy. By the end of this journey, you will know the 35 most baffling cosmic mysteries ever recorded in scientific data. We will encounter a star that dims in impossible ways and a ghostly flow of galaxies pulled by something outside the known universe. What do you believe is the universe's greatest unsolved puzzle? Our journey begins with a single, electrifying mark on a piece of paper. In the quiet of a university office in 1977, astronomer Jerry Amon was reviewing data from the Big Ear radio telescope, a massive instrument patiently listening to the sky. His eyes scanned the columns of letters and numbers, a routine check for anything unusual. Then he saw it, a sequence so powerful, so perfectly tuned, and so utterly out of place that it stopped him cold. He grabbed a red pen and circled the alphanumeric code on the printout. Next to it, he wrote one word in the margin: "Wow." This was the wow signal. For 72 seconds, the telescope had recorded a radio burst from the direction of the constellation Sagittarius that was 30 times stronger than the background noise of deep space. It was a narrowband signal, meaning it was focused on one specific frequency, just like a radio station. And that frequency, 1420 MHz, is a protected band. Here on Earth, it is a quiet channel reserved by international agreement so that no earthly transmitter should be using it. It is a frequency where the universe itself is supposed to be silent. The signal came in, peaked in intensity, and then faded away as the Earth's rotation moved the telescope's gaze. It was never heard again, not once in the decades of searching that followed. That is the core of the mystery. If it was some natural cosmic event, why has nothing like it ever been recorded since? If it was a glitch or some human-made interference, why did it match the exact profile scientists had theorized an intelligent signal might have? The leading natural explanation suggested it could have been emissions from a passing comet, but that theory has been heavily disputed, as comets do not typically emit such strong, narrowband radio waves. The wow signal stands alone. It is the ghost in the machine, a one-time shout into the cosmic dark that we happen to be listening in the right place at the right moment to hear. It remains the purest, most tantalizing piece of data in the search for extraterrestrial intelligence, a single red ink notation that continues to ask a profound question. Were we, for just over a minute, not alone in the universe? That singular wow signal was a whisper compared to the cosmic screams we now know echo across the universe. Fast radio bursts are exactly what their name suggests. They are colossal blasts of radio energy, so intense that for a few thousandths of a second, they outshine entire galaxies. The first one was not heard live. It was found years later, hidden like a fossil in old data recorded by the Parkes Radio Telescope in Australia. A scientist named Duncan Lorimer was sifting through archival observations from 2001 when he spotted a spike so dramatic, so fleeting, he initially thought it was an instrument error. It was a 5-millisecond burst that, based on its dispersion, had traveled billions of light years to reach us. In that brief flash, it unleashed more energy than our sun produces in 80 years. This was not a signal, this was a detonation. Since that retrospective discovery in 2007, astronomers have catalogued hundreds of these events. Their nature is a puzzle wrapped in an enigma. Most appear to be one-time cosmic fireworks erupting from a random point in the sky and never repeating. But a handful defy even that pattern. One source, designated FRB 12112, has been firing off bursts for years from a dwarf galaxy 3 billion light-years away. Its eruptions are chaotic, unpredictable, and immensely powerful. What could possibly be the cosmic engine behind such violence? The most accepted theory points to magnetars, which are the collapsed, hyper-dense cores of dead stars, spinning furiously and wrapped in magnetic fields trillions of times stronger than Earth. A starquake on such a monster, a sudden crack in its crust, could theoretically unleash the energy we see. Yet, the extreme brevity and staggering power of some bursts still push the limits of what magnetars are believed capable of. This gap in understanding is where more speculative ideas emerge. Could these be the signatures of unimaginably advanced technology, like power beams for interstellar light sails? While natural explanations are far more likely, the sheer extremity of fast radio bursts forces science to confront the limits of its knowledge. They are cosmic telegrams written in a language of raw power we are only beginning to decode, reminding us that the universe is far more dynamic and explosive than we ever dreamed. The sheer violence of fast radio bursts is matched only by a star's eerie, silent fading. In the vast archive of data from NASA's Kepler space telescope, citizen scientists with the Planet Hunters project spotted something profoundly wrong with a star 1,400 light-years away. Officially catalogued as KIC 8462852, it became known as Tabby's star after the lead astronomer Tabitha Boyajian. Kepler's mission was to find planets by detecting the tiny, periodic dips in starlight they cause as they transit. A typical dip from a Jupiter-sized world might dim a star by about 1%. The data from Tabby's star told a different story entirely. This star's light didn't just dip. It plummeted. On multiple occasions, the star's brightness dropped by staggering amounts, up to 22%. That is not a planet. That is an object large enough to block nearly a quarter of the star's face. The dips were also chaotic. They were asymmetric, meaning the light would fade quickly and recover slowly, or vice versa. And they were aperiodic, with no regular pattern or predictable timetable. This was not a clockwork solar system. It looked like something was passing in front of the star in a messy, clumpy, and utterly inexplicable swarm. The most famous and sensational hypothesis was that of an alien megastructure. The idea, stemming from Freeman Dyson's thought experiment, suggested an advanced civilization might be building a vast swarm of energy-collecting panels around their star, a Dyson sphere. The irregular dimming could be explained by a partially constructed swarm, with panels and structures of different sizes and shapes drifting in front of the star. While captivating, scientists quickly sought natural explanations. One leading theory proposed a giant swarm of comets, perhaps disrupted by a passing star, creating a thick, dusty cloud. Others suggested it could be the aftermath of a planetary collision, leaving a field of debris. Later observations revealed the dimming was more pronounced in infrared light, a key clue. That pointed toward dust, not solid megastructure material. Dust particles are small and scatter longer, infrared wavelengths more effectively. So the current best guess is a massive, uneven ring of circumstellar dust, possibly from the breakup of a moon or a planet, orbiting the star in a way that creates those bizarre, deep shadows. Yet, the mystery persists because the dust itself does not fully explain the extreme depth and irregularity of the dimming events. Tabby's star continues to behave strangely, its light still flickering in unpredictable ways. It stands as a monument to a powerful truth in modern astronomy. Sometimes the data presents a mystery so compelling that the most outlandish idea becomes a necessary stepping stone, forcing us to question everything we thought we knew about how star systems behave. While Tabby's star flickers from 1,000 light-years away, a different kind of puzzle was unfolding much closer, within the very boundaries of our own solar system. It involved not something seen, but something felt, a phantom force acting on humanity's earliest interstellar messengers. The Pioneer anomaly began as a whisper in the data, a tiny discrepancy that grew into a decade-spanning mystery. After their historic flybys of Jupiter and Saturn, the Pioneer 10 and Pioneer 11 spacecraft were on escape trajectories, sailing into the abyss beyond the planets. By the early 1990s, scientists meticulously tracking their radio signals noticed something was off. The Doppler shift in the signals, which tells us exactly how fast a spacecraft is moving, indicated both probes were slowing down slightly more than they should have been. It was an almost imperceptible deceleration, a constant sunward tug equivalent to about 1/10 billionth of the gravity you feel on Earth's surface. But in the precise world of orbital mechanics, where calculations account for the gravity of every planet and the pressure of sunlight itself, this minuscule drift was a glaring error. It was as if an invisible hand was gently applying the brakes. For years, this anomaly fueled intense speculation. Could it be evidence of new physics, a flaw in Einstein's theory of general relativity at the largest scales? Some wondered if it was a local effect of dark matter, a halo of unseen particles gravitationally dragging on the spacecraft. The idea that our understanding of gravity itself might be incomplete was electrifying. Solving the mystery, however, required a monumental forensic effort. Teams of scientists spent years recovering and analyzing decades of old telemetry data, reconstructing the thermal and electrical history of the two distant probes. The breakthrough came not from looking outward into the cosmos, but inward at the spacecraft's own design. Both pioneers were powered by radioisotope thermoelectric generators, which produce electricity from the heat of decaying plutonium. That heat had to go somewhere. The team realized that the spacecraft were radiating this waste heat anisotropically, meaning not evenly in all directions. More heat was emitted from the back of the dish-shaped spacecraft, the side facing away from the Sun and Earth. According to the simple physics of thermal radiation, photons carrying that heat away also impart a tiny amount of momentum. This created a minute but constant thrust pushing the spacecraft back toward the Sun. It was not a mysterious pull from the universe, but a gentle push from within. When this thermal recoil force was finally modeled with exquisite detail, accounting for the exact power output over the mission's lifetimes, the anomalous deceleration vanished. The Pioneer anomaly was solved, yet its legacy is profound. It stands as a masterclass in scientific detective work, showing how a ghost in the machine can lead researchers on a hunt spanning millions of miles and decades of time. It reminds us that before we invoke dark matter or new laws of physics, we must first become intimately acquainted with our own machinery. The solution was mundane, but the path to it was anything but a testament to the power of persistent curiosity in the face of a stubborn data point. The solved mystery of the Pioneer probes gave us confidence in our local physics, but that confidence was about to be shattered by a discovery on the largest scale imaginable. It is called the dark flow, and to understand its terrifying implication, you must first picture the universe not as a collection of stars, but as a fundamental background glow. This is the cosmic microwave background, the ancient afterglow of the Big Bang, a snapshot of the infant universe when it was just 380,000 years old. It is the most perfect thermal bath in existence, bathing the entire cosmos in microwaves. For decades, we have mapped its subtle temperature variations, tiny hot and cold spots that are the seeds of all future galaxies. These maps, like the one from the Wilkinson Microwave Anisotropy Probe, are supposed to be our ultimate reference frame. They tell us how the universe is expanding and how matter is distributed. But in 2008, a team of scientists led by Alexander Kashlinsky looked at this data in a revolutionary new way. They were not just studying the CMB itself. They were studying how the CMB light appeared to be shifted by the motion of massive galaxy clusters moving through space. This is the kinematic Sunyaev-Zeldovich effect, a mouthful that simply means a moving cluster of galaxies leaves a faint, specific fingerprint in the microwave background. What they found was not just random motion. They analyzed the data for over 700 massive clusters and discovered they were all streaming like leaves caught in a cosmic river in the same direction. And they were moving fast at a staggering speed of over 600 kilometers per second. This was not due to the expansion of the universe. That expansion is smooth and uniform in all directions. This was a directed flow, a coherent motion of thousands of galaxy clusters across billions of light years, all pulled toward a single point in the sky near the constellations Centaurus and Vela. The sheer scale is incomprehensible. This flow extends to the very edge of our observable universe, meaning whatever is causing it must lie beyond that edge. The gravitational pull required to move so much mass is unimaginable. It suggests the presence of something colossal, a structure or mass so vast it makes our entire visible cosmos seem like a neighborhood in a far greater metropolis. The most profound and controversial explanation is that this dark flow is the gravitational tug of another universe entirely, a neighboring bubble in an infinite multiverse brushing up against our own. Of course, skepticism followed. Later data from the more precise Planck satellite was analyzed, with some teams arguing the signal was a statistical artifact or caused by incomplete data processing. Yet other analyzers, including more recent ones, continue to support the original finding. The debate is fierce because the stakes are existential. The dark flow, if real, is our first potential empirical clue that our universe is not alone. It is a ghostly current in the cosmic sea, pointing toward a shore we cannot see, hinting that everything we know is just a small island in an ocean of realities beyond our comprehension. If the dark flow hints at a universe beyond our own, then the Fermi bubbles are a monument to a cataclysm within our own galactic home. Rising from the heart of the Milky Way like two colossal, ghostly balloons, these structures are a stark reminder that our galaxy has not always been the quiet spiral it appears to be today. Their discovery was not the result of peering through an eyepiece, but of patiently sifting through the most energetic light in the universe. When scientists first processed the all-sky survey data from NASA, a Fermi gamma-ray space telescope in 2010, they expected to see the diffuse glow of gamma rays from cosmic rays colliding with interstellar gas. What they found was something entirely new and breathtaking in scale. Emerging from the galactic center, perpendicular to the starry disk, were two immense lobes of gamma-ray emission. Each bubble stretches an astonishing 25,000 light-years from the galactic plane. To grasp that size, picture our entire solar system. From the Sun to the edge of its gravitational influence is about 1 light-year. Now multiply that by 25,000. One of these bubbles would span the distance from Earth to the center of the galaxy and far, far beyond. They are pristine and symmetrical, with remarkably sharp edges, like two identical soap bubbles blown from a single cosmic wand. The gamma rays that outline them are not the product of normal starlight. They are the signature of something immensely violent, the afterglow of particles accelerated to nearly the speed of light. So what event could have carved such perfect, energetic structures into the fabric of our galaxy? Astronomers have two leading suspects, both pointing to a dramatic outburst millions of years ago. The prime candidate is our galaxy's own supermassive black hole, Sagittarius, a star. While it is quiet today, it may have had a tumultuous past. A period of intense feeding, as vast clouds of gas fell into its maw, could have triggered a titanic eruption. Twin jets of matter and energy screaming out from the black hole's poles at relativistic speeds might have inflated these giant bubbles, pumping them full of high-energy particles that still glow in gamma rays. The other possibility is a frenzy of star formation in the galactic center. If millions of stars were born in a short, explosive period, the combined effect of their powerful stellar winds and subsequent supernova explosions could have blown a giant bipolar bubble into the surrounding gas. The truth is, we do not know which event, or perhaps a combination of both, is responsible. The exact trigger and timing remain locked in the bubble's faint glow. They are a silent echo of a time when the heart of our Milky Way was a place of unimaginable fury, a ghostly imprint in gamma-ray light that forces us to rewrite the biography of our own cosmic neighborhood. The colossal Fermi bubbles remind us of our galaxy's violent past, but they are not the only force guiding its journey. Our entire galactic neighborhood is caught in a vast and relentless current, pulled toward a point of unimaginable gravity hidden behind a cosmic veil. This is the mystery of the Great Attractor. For decades, astronomers mapping the motions of galaxies made a startling discovery. While the universe is expanding in all directions on a local scale, something else is happening. Our Milky Way, along with the entire local group of galaxies and the immense Virgo supercluster it belongs to, is all streaming in the same direction. We are not drifting aimlessly, we are falling. Velocity maps created from immense surveys of hundreds of thousands of galaxies reveal this coherent flow like leaves swept into a drain. The destination of this cosmic river is a gravitational anomaly roughly 220 million light-years away, in the direction of the southern constellation Norma, the Carpenter's Square. The gravitational pull required to move so many galaxies is staggering, equivalent to the mass of tens of thousands of Milky Ways, but here lies the core of the mystery. This target region, the heart of the Great Attractor, lies directly behind the dense plane of our own galaxy. This area is known to astronomers as the zone of avoidance. It is a thick band of interstellar gas, dust, and countless stars that completely obscures our optical view, like trying to see a distant city through a dense, permanent fog. For a long time, the Great Attractor was a phantom, a gravitational signature with no visible source. The breakthrough came when astronomers turned to instruments that could see through the dust. Using radio, infrared, and X-ray telescopes, we began to pierce the veil. What we found behind the zone of avoidance was not a single, monstrous object, but an incredibly dense knot of the cosmos. We discovered the Norma cluster, a massive congregation of galaxies, and the even larger Laniakea supercluster, of which we are an outlying part. Laniakea, which means immense heaven in Hawaiian, is our true cosmic address, a filamentary web of galaxies spanning 500 million light-years, all flowing toward its gravitational center near the Great Attractor region. So is the mystery solved? Not entirely. While the combined mass of the Norma cluster and the surrounding Laniakea supercluster is immense, some calculations suggest it may still not be enough to account for the full strength of the observed pull. This leaves a tantalizing possibility. Could there be something even denser and darker hidden within that zone, something our instruments have yet to fully reveal? The Great Attractor may not be a single lurking monster, but its lingering gravitational puzzle ensures it remains one of the most profound reminders that much of the universe's true structure is still hidden from our sight, pulling us toward discoveries we have only begun to sense. The Great Attractor pulls us toward a hidden mass, but in 2017, an object arrived from a place of total obscurity, moving too fast to belong here at all. It was the first confirmed visitor from another star system, a dark, tumbling rock named Oumuamua, a Hawaiian word meaning scout or messenger. Telescopes around the world scrambled to track it as it slingshotted around the sun and began its permanent exit from our solar system. The initial data was bizarre enough. Its light curve, the pattern of its brightness as it spun, suggested an extreme shape, perhaps 10 times longer than it was wide, like a cosmic cigar or a flattened pancake. But the true enigma emerged in the precise astrometric measurements of its path. As Oumuamua sped away, something was wrong. Its trajectory could not be perfectly explained by the gravitational tug of the sun and planets alone. The data showed a clear, tiny, but statistically significant acceleration. It was as if an invisible hand was giving it an extra, gentle push out the door. Scientists immediately turned to the most common explanation for such non-gravitational motion in space: outgassing. When a comet approaches the sun, its icy surface heats up, releasing jets of gas and dust that act like natural thrusters. This is a well-understood process. The problem was, Oumuamua showed no visible coma, the fuzzy cloud of gas and dust that always surrounds an active comet. Our most powerful telescope saw no hint of outgassing debris, no tail streaming behind it. It presented a stark, bare profile against the stars. So if it was outgassing to cause the acceleration, it had to be doing so in a way that released gas without releasing any detectable dust, a behavior completely unlike any comet we have ever seen. This glaring contradiction opened the door to more exotic possibilities. A team of astronomers led by Avi Loeb proposed a different mechanism. What if the acceleration was caused by radiation pressure from the sun itself? Photons, the particles of light, carry a tiny amount of momentum. When they strike an object, they push it, just like wind pushes a sail. For this to explain Oumuamua's acceleration, the object would need to be extraordinarily thin and light, with a huge surface area relative to its mass. It would need to be, in essence, a light sail. In nature, such a structure could conceivably form from the debris of a shredded planet or through other violent processes, creating a slab of material perhaps just a fraction of an inch thick. The more controversial interpretation, which Loeb famously entertained, was that such a shape and behavior were consistent with an artifact of technology, a discarded piece of an alien light sail drifting between the stars. The scientific community remains deeply divided. Many experts strongly favor a natural origin, suggesting Oumuamua was a very unusual type of comet, perhaps one coated in a thick, carbon-rich crust that allowed only pure gas to seep out from specific cracks, explaining the lack of dust. Others propose it could be a fragment of a Pluto-like world, a shard of solid nitrogen blasted away in some ancient cataclysm. The fundamental challenge is that we had only a few weeks of frantic observations before the visitor faded forever from view. We are left with a single, enigmatic data set, a handful of clues from a passerby that will never return. Oumuamua's legacy is not a solved mystery, but a profound lesson. It revealed that interstellar objects are real and that they can possess properties that defy our immediate catalog of known things. It underscored that when the universe sends us a messenger, we must be prepared for it to speak in a language we do not yet fully understand. Oumuamua's solitary journey challenged our categories, but a discovery within a faint smudge of light threatened to dismantle a foundational pillar of modern cosmology. For decades, astronomers have operated on a core principle: dark matter is the invisible scaffolding of the universe. This mysterious substance, which does not emit or interact with light, provides the extra gravitational glue needed to hold galaxies together. Without its immense, unseen halo, the visible stars in a spiral galaxy like our Milky Way would simply fly apart, their rotation speeds too great for the gravity of ordinary matter alone to contain. This model has been spectacularly successful, explaining the motions of galaxies across the cosmos. Then, in 2018, a team led by Pieter van Dokkum of Yale University pointed the Hubble Space Telescope and other instruments at a ghostly galaxy 44 million light-years away, known as NGC 1052 DF2. What they found was not just surprising, it was heresy. DF2 is an ultra-diffuse galaxy, a wispy, translucent collection of stars so sparse you can practically see right through it. The team measured the motions of 10 bright globular clusters, the dense balls of stars that orbit the galaxy's core. The speed of these orbiting clusters acts as a cosmic scale, revealing the total mass, both visible and dark, pulling on them. The results were unequivocal and shocking. The clusters were moving slowly, lazily, at speeds that could be entirely accounted for by the gravitational pull of the galaxy's visible stars alone. There was no need for, and no sign of, a dark matter halo. This was like finding a car speeding down the highway without an engine. The very ingredient thought to be essential for a galaxy's birth and survival was simply missing. The immediate reaction from the scientific community was intense skepticism. Could the measurements be wrong? Could the galaxy be closer or farther than estimated, throwing off the calculations? Follow-up observations, however, only reinforced the initial findings. DF2 truly appeared to be a galaxy of pure, ordinary matter. This single data point created a monumental paradox. If dark matter is mandatory for galaxy formation, how did DF2 even come to exist? One leading theory suggests a violent history. Perhaps it was born within a rich cluster of galaxies and repeated close encounters with a massive neighbor, like the giant elliptical galaxy NGC 1052, stripped away its dark matter halo through immense tidal forces, leaving behind the bare skeleton of stars we see today. Another, more radical interpretation questions our understanding of gravity itself. The theory of modified Newtonian dynamics, or MOND, proposes that on the vast scales of galaxies, gravity behaves differently than Newton or Einstein predicted, eliminating the need for dark matter entirely. In a MOND universe, a sparse galaxy like DF2 would naturally have slower moving stars. This single, faint smudge of light has become a cosmic battleground, a profound outlier that forces us to confront two equally staggering possibilities. Either galaxies can, against all odds, form without the dark matter we thought was essential, revealing a universe more diverse in its recipes than we imagined, or our fundamental grasp of gravity, the force that governs the cosmos, requires a radical rewrite. DF2 is not just a missing puzzle piece. It is a piece from a different puzzle altogether, asking us which picture we are really trying to solve. The ghostly galaxy DF2 defies the rules of gravity, but another anomaly is etched into the very first light of creation. The cosmic microwave background is the oldest photograph of the universe, a snapshot from when it was just 380,000 years old. This afterglow of the Big Bang is almost perfectly uniform, bathing the cosmos in microwhales at a frigid temperature of just 2.7 degrees above absolute zero. But when scientists created exquisitely detailed maps of this background using satellites like Oumuamua and Planck, they noticed something strange. One particular patch of sky in the constellation Eridanus was noticeably, inexplicably colder than the rest. This is the cold spot. It is not a tiny blemish. This region spans a staggering 1 billion light-years across, a colossal circular patch of the sky that is about 70 microkelvins colder than the average surrounding temperature. In a sea of near-perfect uniformity, this is a profound statistical outlier. The chance of such a large, cold region appearing randomly in the cosmic microwave background is incredibly slim, less than 1 in 200. It is a feature that demands an explanation, a cosmic bruise on the infant universe. So what could have left such a mark? One leading theory points to a cosmic supervoid. Imagine the CMB light as a traveler on an epic journey. As light climbs out of a gravitational well, like the space near a massive galaxy cluster, it loses energy, shifting to longer, redder wavelengths, a phenomenon called gravitational redshift. Conversely, if light falls into a void, a vast region of below-average density, it gains energy, shifting slightly bluer. But when it climbs back out of that void on the other side, it loses that energy again. If the void is deep and large enough, the net effect is an energy loss. The light emerges slightly colder, imprinting a cold spot on the CMB map. Intriguingly, astronomers have indeed found a large, sparse region of space, known as the Eridanus supervoid, roughly aligned with the cold spot. The problem is one of scale. The void we have found, while enormous, appears to be about 10 times too small to account for the extreme temperature drop we observe. It is like finding a pothole to explain the crater from a meteorite strike. This discrepancy has fueled a more exotic possibility. Could the cold spot be a cosmic texture? In the frenetic first moments after the Big Bang, as the fundamental forces of nature were settling into their current states, physicists believe topological defects might have formed in the fabric of spacetime itself. These defects, called textures, would be knots of concentrated energy. If a texture existed within our observable universe, it would leave a distinct circular imprint on the cosmic microwave background, a signature chillingly similar to what we see. The cold spot, therefore, stands at a crossroads. It is either evidence of the largest known structure of nothingness in the universe, a void so vast it challenges our models of cosmic structure, or it is a fossilized relic from the universe's first split second of existence, a scar from a phase transition that shaped reality itself. Either answer reshapes our cosmic story, proving that even in the universe's oldest light, mysteries are waiting to be decoded. While the cold spot chills the ancient sky, our telescopes trained on a different spectrum of light are finding objects that simply shouldn't be there. Deep within the dusty heart of our galaxy and scattered across infrared sky surveys, astronomers have catalogued thousands of mysterious pinpricks of heat that defy explanation. They are called unidentified infrared objects, or UIRO for short. To understand their strangeness, you have to think of the universe in colors of light our eyes cannot see. Optical telescopes show us the familiar universe of stars and galaxies, shining invisible light, but much of the cosmos is hidden behind veils of cold, dark dust that blocks this light entirely. Infrared telescopes, however, peer right through that dust. They see the heat glow of objects too cool or too shrouded to shine visibly. The Spitzer Space Telescope and the Wide Field Infrared Survey Explorer, WISE, have mapped the sky in this thermal vision, creating a census of cosmic warmth. Most sources have clear counterparts, a hot young star, a distant galaxy, a cloud of gas, but a persistent population of objects does not. These UIRO blaze brightly in the infrared, yet when astronomers point the most powerful optical telescopes at those exact coordinates, they see nothing at all. Complete darkness. It is as if these objects only exist in the world of heat. Their spectral energy distribution, the fingerprint of their light across different wavelengths, is bizarre. It peaks strongly in the mid-infrared and then falls off in a way that doesn't match any known type of star, planet, or galaxy. They are unresolved, meaning they appear as single points of light, not extended structures ruling out distant galaxies. So what exactly is glowing so warmly in the void? The hunt for an answer has led to several compelling candidates, each stranger than the last. One strong possibility is that we are seeing the faint embers of failed stars. Brown dwarfs are objects too massive to be planets, but not massive enough to ignite sustained hydrogen fusion in their cores. They form like stars but then cool and fade, radiating most of their energy as infrared heat. A particularly cold, ancient brown dwarf drifting in interstellar space could perfectly match the profile of a UIRO. Another fascinating idea points to the very beginnings of solar systems. A protoplanetary disk in its earliest, most embedded stage is a thick, swirling cocoon of gas and dust surrounding a newborn star. The central star might be completely hidden, but the disk itself, heated by the star's buried energy, would glow intensely in the infrared. We could be witnessing the birth chambers of planets, their construction sites so thick with material that not a single photon of visible light escapes. Then there are the more exotic proposals. Could some UIRO be quark stars? These are theoretical stellar remnants even denser than neutron stars, where the fundamental particles themselves break down. The decay of exotic matter within them might produce a unique infrared signature. Or perhaps they are rogue planets, giant worlds ejected from their solar systems and wandering the cold interstellar dark, still warm from their violent formation. The profound implication of the UIRO mystery is not necessarily any one of these explanations, but their collective existence. They represent an entire hidden population of celestial objects that our current classification boxes star, planet, galaxy cannot neatly contain. They are the unknowns in our infrared census, reminding us that for every brilliant star we see, there may be a dozen faint, warm ghosts drifting unseen, their true nature still waiting to be decoded. The hidden warmth of Uero speaks of unseen populations, but in our own cosmic backyard, a different census reveals a sudden and puzzling emptiness. Far beyond the orbit of Neptune, in the deep freeze of the solar system's outskirts, lies the Kuiper Belt. This is a vast donut-shaped region populated by icy remnants from the dawn of the planets, dwarf worlds like Pluto and Eris, and countless smaller frozen bodies. For decades, astronomers have been meticulously counting these distant objects, mapping the population of this frozen frontier. The data from ambitious surveys like the Outer Solar System Origin Survey (OSOS) has painted a clear and startling picture. The number of objects does not gradually dwindle as you go farther out, as most models predicted. Instead, there is a sharp, clean edge. At a distance of roughly 50 astronomical units from the Sun, about 50 times the Earth-Sun distance, the Kuiper Belt population falls off a cliff. This is the Kuiper Cliff. Beyond this boundary, the vast reservoir of icy material seems to simply vanish. It is as if the solar system has a fence, and on the other side, the yard is nearly empty. This is profoundly unexpected. Our standard models of how the solar system formed suggest this primordial debris disk should extend much farther, fading slowly into the Oort cloud. The cliff suggests something happened, something that violently sculpted the outer edge of our planetary system. So what could have carved this sharp boundary? One compelling theory points to the gravitational influence of a massive, unseen world. The hypothetical planet 9, a potential super-Earth lurking hundreds of astronomical units out, could have shepherded the Kuiper Belt objects during the solar system's chaotic youth. Its immense gravity might have swept the region beyond 50 clean, either flinging objects inward toward the Sun or ejecting them into interstellar space entirely, leaving behind this stark drop-off. Another dramatic possibility involves a visitor from the depths of interstellar space. In the solar system's infancy, a passing star could have ventured perilously close. The gravitational tides from such a flyby would have been catastrophic, stripping away the outer layers of the primordial disk like a cosmic thief, stealing the material that should have formed the belt's distant reaches and leaving us with this abrupt edge today. Yet, confirming any of this is a monumental challenge. Observing objects at such extreme distances is pushing the limits of our technology. At 50 and beyond, sunlight is incredibly faint, and these icy bodies are dark. They reflect almost no light, making them needles in a cosmic haystack. Every new discovery in that zone is a triumph of patience and precision. The Kuiper Cliff, therefore, is more than just a data point on a graph. It is a silent witness to a turbulent past, a forensic clue etched into the orbital distribution of frozen worlds. It tells us that the calm, orderly solar system we see today is the product of a much more dynamic and possibly violent history, where gravitational giants, either native or passing, once roamed and reshaped our celestial neighborhood, leaving behind this empty frontier as their only signature. This sharp edge of our solar system marks a boundary of missing matter, but cosmologists face a far grander accounting problem on the scale of the entire cosmos. It is called the missing baryon problem, and it begins with a simple, profound inventory. Baryons are the particles that make up the ordinary, tangible stuff of our world, the protons and neutrons in every atom of every star, planet, and galaxy. We know with incredible precision from studying the cosmic microwave background exactly how many baryons were forged in the Big Bang. It is a definitive number, a cosmic ledger entry from the universe's first moments. So we should be able to find them all today. The task should be as simple as counting every star, every wisp of interstellar gas, every speck of dust across the heavens. Yet, when astronomers perform this cosmic census, the books do not balance. They come up short, drastically short. About 30 to 40% of all the ordinary matter that should exist in the present-day universe is simply missing from our tallies. It is not dark matter, that separate, mysterious substance. This is the regular atoms we are made of that have seemingly vanished. Where could half the universe's normal atoms possibly go? The leading suspect is not a place, but a state of being. Theorists believe the missing baryons are not in galaxies at all, but in the vast, empty deserts between them. In the immense cosmic web, where filaments of dark matter scaffold the universe, ordinary matter is thought to be pulled along, collecting into these faint threads. There, it is heated by the shock waves of collapsing galaxy clusters and the fierce radiation from quasars to temperatures of hundreds of thousands, even millions of degrees. This creates what is known as the warm-hot intergalactic medium, or WIM. Think of it as a cosmic steam, a superheated, incredibly thin fog filling the spaces in the grand cosmic architecture. This gas is so diffuse and so hot that it is nearly invisible. It does not glow in visible light, and its primary signature is in very specific, faint lines in the far ultraviolet and soft X-ray parts of the spectrum. Detecting it is like trying to see the heat haze above a distant desert road from orbit. The hunt for this missing matter has become a premier challenge for modern observatories. Scientists use brilliant, distant beacons known as quasars as cosmic flashlights. As the quasar's light travels billions of light years to reach us, it passes through these invisible filaments of the WIM. Atoms within the hot gas absorb very specific wavelengths of that light, leaving minuscule, telltale dips in the quasar's spectrum. It is forensic astronomy on the largest scale. Missions like the Hubble Space Telescope with its sensitive ultraviolet eye and the Chandra X-ray Observatory have begun to find these fingerprints. They have detected the absorption signatures of highly ionized oxygen and other elements in the lines of sight to quasars, confirming that these vast reservoirs of million-degree gas do exist, woven through the voids. Each detection is a small recovery of the universe's lost ledger entry. The mystery of the missing baryons is slowly being solved, not by finding new objects, but by learning to see the invisible, seething ocean in which all galaxies float. It is a reminder that the universe's most fundamental components are often hidden in plain sight, waiting for us to develop the vision to perceive them. Recovering the universe's missing atoms is a triumph of modern cosmology, yet it rests on a foundational belief now facing a strange challenge from the oldest light. The cosmic microwave background should be the ultimate proof of a featureless, directionless cosmos. According to the bedrock cosmological principle, the universe is isotropic and homogeneous on the largest scales. No direction should be special. The CMB maps from Oumuamua and Planck are the strongest evidence we have for this, showing a near-perfect thermal bath. But when scientists probed deeper into the statistics of that ancient light, they found something that made them profoundly uneasy. They called it the axis of evil. This provocative name refers to a bizarre and unexpected alignment in the largest patterns of the CMB. To understand it, think of the microwave sky not as a uniform glow, but as a mosaic of hot and cold spots of different sizes. Scientists describe these patterns using mathematical terms called multipoles. The dipole is the largest pattern caused by our motion through the cosmos. The quadrupole and octupole are the next largest patterns, vast warm and cool regions stretching across billions of light years. These immense patterns should be oriented randomly, pointing in directions that have absolutely no relationship to each other or to anything in our local neighborhood. The shocking discovery was that they are not random at all. The planes of the quadrupole and octupole moments appear to be aligned with each other. Even more bizarrely, this combined alignment also seems to correlate with the plane of our own solar system, the ecliptic, and even the direction of the sun's motion through the galaxy. The probability of this happening by sheer cosmic chance is incredibly low, less than 1 in 1,000. It is as if the largest structures in the infant universe are somehow aware of the insignificant orientation of our tiny planetary system, a correlation that makes no physical sense. The immediate and most likely explanation is not a cosmic conspiracy but contamination. Our view of the pristine CMB is filtered through a fog of foreground emission from within our own Milky Way. Light from interstellar dust, synchrotron radiation from electrons spiraling in magnetic fields, and other local effects must be meticulously subtracted from the raw satellite data to reveal the true cosmic signal. Perhaps the models used to clean this foreground are imperfect, leaving behind a subtle, structured residue that mimics this strange alignment. Teams have spent years trying to rule this out, developing ever more sophisticated techniques to isolate the CMB. Yet the alignment stubbornly persists in the clean data. If it is not a data processing artifact, the implications are staggering. It would suggest the universe has a preferred direction, a subtle but real axis on the grandest scale, violating the principle of isotropy that underpins almost all of modern cosmology. It would mean that one direction in space is fundamentally different from another, that the cosmos has a grain like wood and we can see its alignment. While most cosmologists believe a local, systematic error will eventually be found, the axis of evil stands as a profound cautionary tale. It reminds us that our most sacred maps of the cosmos are interpretations, and that sometimes the ghosts in our own machinery can whisper secrets that shake the foundations of reality itself. An axis in the ancient sky hints at a fundamental grain to the cosmos, yet a different, more colorful mystery points to the very ingredients of existence. In the constellation Monoceros, the unicorn, a dying star has woven a celestial tapestry of breathtaking symmetry. Known as the Red Rectangle Nebula, it appears through telescopes as a stunning geometric form, a glowing box with ladder-like rungs of crimson light, a structure so perfect it looks almost artificial. But its true secret is not in its shape, but in the specific colors of its light, a fingerprint that has defied identification for half a century. When astronomers break the nebula's light into its constituent wavelengths, creating its spectrum, they find a series of sharp, bright emission bands in the infrared. These are not the familiar signatures of common atoms like hydrogen or helium. They are a set of 4 distinct spikes at very specific, unchanging wavelengths, known universally as the Unidentified Infrared Emission Bands or UIE band. The red rectangle is their most famous source, but they appear throughout the galaxy, in the spectra of other nebulae, and even in the space between stars. They are a cosmic barcode that our laboratories cannot yet scan. For decades, astrophysicists have hunted for the molecule or material that produces this exact pattern. It is a spectral signature that must come from something vibrating or rotating at a very specific energy. The leading suspect for years has been a class of large, robust organic molecules known as polycyclic aromatic hydrocarbons or PAHs. Think of them as tiny flakes of soot, flat sheets of carbon atoms arranged in hexagonal rings, like microscopic pieces of chicken wire. When ultraviolet light from a star strikes these molecules, they vibrate and emit infrared light at characteristic wavelengths. The problem is, while PAH spectra in the lab come close, they do not provide a perfect one-to-one match with the 4 mysterious red rectangle bands. The search has expanded to even more exotic carbon structures. Could the carrier be something like Buckminster fullerene, a soccer ball-shaped cage of 60 carbon atoms known as C60? This molecule, nicknamed a buckeball, has been found in space, and its infrared fingerprints share some similarities. Yet again, the exact match remains elusive. This makes these glowing bands a kind of holy grail in laboratory astrophysics. They are a direct message from the interstellar medium, telling us that complex organic chemistry is not just happening on planets, but is rampant in the cold vacuum of space itself. The molecule that produces these bands is likely a large, stable, and very common form of carbon-based matter. Solving this spectral riddle would be like finally identifying a fundamental pigment in the cosmic palette, revealing one of the most abundant carriers of organic carbon in the galaxy. It could show us the raw materials that were delivered to the early Earth, the very seeds from which the chemistry of life might have sprung. The red rectangle's beautiful geometry is a facade. Its true gift is this encrypted message in infrared light, a persistent, universal signal that we have yet to fully translate. The geometric glow of the red rectangle hides a chemical mystery, but another anomaly is said to orbit much closer to home, wrapped in layers of modern myth. The legend of the Black Knight satellite is a tangled web of fact and fiction, a story that began not with a sighting but with a sound. In the late 19th century, the brilliant inventor Nikola Tesla was experimenting with his powerful wireless transmitter in Colorado Springs. He reported picking up strange, rhythmic radio signals he could not explain, a series of repeating clicks that he speculated could be an attempt at communication from another world. Decades later, in the 1920s and 30s, other radio pioneers, including a Norwegian engineer named Jørgen Hauls, reported similar unexplained long-delayed radio echoes. These were signals that seemed to bounce back from space with a delay that suggested an origin far beyond the ionosphere, from something that should not have been there. These odd auditory events are the first legitimate data points in the Black Knight saga, genuine anomalies recorded by serious scientists. The story truly captured the public's imagination in the 1960s, however, with the grainy photographs. During the early days of the Corona spy satellite program, which used film capsules ejected from orbit and recovered mid-air, imagery occasionally captured unidentified specks against the backdrop of Earth. One particular frame, showing a dark, irregular object in what appeared to be a polar orbit, was later seized upon by UFO researchers as proof of the Black Knight, an ancient alien satellite watching over Earth. The most famous image associated with the myth, a dark, tumbling object photographed during a space shuttle mission, provided a seemingly modern confirmation. So what is really going on? The most plausible explanations are remarkably mundane, yet they perfectly illustrate how mysteries are born from ambiguity. The strange radio echoes heard by Tesla and others are now widely attributed to natural phenomena that were not understood at the time, such as whistlers caused by lightning, or the newly discovered Van Allen radiation belts interacting with radio waves. As for the objects in the photographs, they are almost certainly human-made debris. The space around Earth is a junkyard of discarded rocket stages, lost thermal blankets, and fragments from old missions. A piece of multilayer insulation from a satellite tumbling end over end can appear as a dark geometric shape. The iconic shuttle photo was later identified as a thermal blanket that had been accidentally lost during a spacewalk. The Black Knight endures not because the evidence is strong, but because the human mind excels at pattern recognition. We connect disparate dots across decades, a radio signal here, a blurry photo there, and weave them into a single compelling narrative. It serves as a powerful case study in how a few genuine, unexplained data points, when filtered through hope and imagination, can crystallize into a legend that outlasts its prosaic explanations. The mystery's true lesson is about us, revealing our deep desire for the cosmos to be not just vast, but inhabited, and our tendency to see messengers in the mundane debris of our own exploration. While the Black Knight is a legend born from earthly debris, a different spacecraft captured a geometric wonder that is undeniably, spectacularly real. Circling the gas giant Saturn, the Cassini probe's cameras stared down at the planet's north pole and sent back an image that defied all expectation. There, whirling in perpetual twilight, was a perfect colossal hexagon. Each of its 6 sides is longer than the entire diameter of our home planet. This is not a trick of perspective or a transient storm. It is a permanent, towering jet stream, a 6-sided hurricane etched into Saturn's atmosphere for at least the last 4 decades, since Voyager first glimpsed it in the 1980s. The data from Cassini's composite infrared spectrometer and imaging team revealed this structure in stunning detail. It is a wall of cloud, a sheer cliff of raging wind where the atmospheric bands outside the hexagon move at a different, slower speed than the furious vortex trapped within its geometric borders. The wind screams along the hexagonal path at over 300 kilometers per hour. How can a fluid, a chaotic gas giant's atmosphere, organize itself into such a stark, angular shape? The answer lies not in alien architecture, but in the elegant and often counterintuitive physics of rotating fluids. On Earth, we see circular hurricanes and swirling eddies. But in the laboratory, when a fluid is rotated at different speeds at its center and its outer edge, something remarkable happens. Scientists have recreated this in tanks of water. As the rotation increases, the circular flow within the tank can spontaneously break into a stable polygon, a square, a pentagon, or most commonly, a hexagon. It is a standing wave pattern, a stable resonance that emerges from the complex interplay between the planet's deep internal rotation and the shallower, faster-moving winds in its upper atmosphere. Saturn's hexagon is likely a colossal, three-dimensional version of this lab experiment, a planetary-scale demonstration of fluid dynamics. Yet, the mystery deepens with two haunting questions. First, why is it only at the North Pole? Cassini's view of the South Pole showed only a more conventional, though still massive, hurricane with an eye wall. The asymmetry suggests something unique about the Northern Hemisphere's atmospheric structure, or perhaps its deeper internal flows. Second, why a hexagon? The specific geometry suggests a very particular and stable resonance condition, a precise balance of forces that has held for generations. It is a beautiful, violent puzzle, a piece of celestial geometry spinning in the deep cold, proving that the greatest wonders are not always beyond our reach, but sometimes orbiting right next door, waiting for us to look. Saturn's geometric perfection is sculpted by fluid laws we can understand, but from the depths of intergalactic space come projectiles that defy the very laws meant to contain them. They are called ultra-high-energy cosmic rays, and they are the universe's most powerful natural bullets. Cosmic rays are typically protons or atomic nuclei, constantly raining down on Earth from space. Most have modest energies, but a tiny fraction, detected by immense observatories like the Pierre Auger Array in Argentina, carry an energy that is almost incomprehensible. We are talking about particles with energies exceeding 10 to the power of 20 electron volts. A single one of these subatomic specks carries the kinetic energy of a professionally thrown baseball, all compressed into a particle smaller than an atom. This energy is millions of times greater than anything the most powerful particle colliders on Earth can produce. According to our best physics, these particles should not be able to reach us. This is because of a fundamental roadblock known as the Greisen-Zatsepin-Kuzmin cutoff, or the GZK cutoff. The universe is not empty. It is filled with the faint bath of the cosmic microwave background, the ancient afterglow light. For a proton traveling at over 99.9999% the speed of light, this microwave radiation is no longer a gentle warmth. It is blue-shifted into a barrage of high-energy gamma rays. When the ultra-high-energy proton smashes into one of these gamma-ray photons, it creates new particles, sapping its own energy in the process. Over a distance of about 150 million light-years, this process should drain these cosmic rays of their extraordinary power. They should be reduced to mere shadows of themselves long before they cross the vast intergalactic voids to reach us. The data tells a different story. We detect them anyway. This means they cannot have come from very far away. They must be produced in our cosmic backyard within a relatively local volume of space. So where in our local universe are the cosmic particle accelerators capable of this feat? The hunt has focused on the most violent engines we know. Supermassive black holes at the hearts of active galaxies can blast out jets of plasma at near light speed, potentially capable of accelerating particles to these extremes. Cataclysmic collisions between neutron stars, events that shake spacetime itself, are another prime suspect. Yet, when astronomers trace the incoming paths of these ultra-high-energy cosmic rays back into the sky, they find no obvious smoking gun. No brilliant quasar or recent merger sits perfectly aligned with their arrival direction. The sources remain hidden, cloaked, or perhaps so brief and erratic that we have not caught them in the act. To even detect these rare events requires science on a monumental scale. The Pierre Auger Observatory, for instance, does not look up. It looks out across a 3,000 square kilometer grid of detectors on the ground. When an ultra-high-energy cosmic ray strikes the upper atmosphere, it triggers a cascading avalanche of secondary particles, a vast shower that spreads out as it falls to Earth. This shower lights up hundreds of the observatory's water tank detectors simultaneously, allowing scientists to reconstruct the original particle's energy and rough direction. Each detection is a monumental effort to catch a single, impossibly powerful mote from a storm we cannot see. These particles are nature's ultimate mystery accelerators, operating at energies that border on the impossible, firing their ammunition from hidden bases somewhere in the local cosmos, challenging us to find the invisible cannons before the next shot arrives. If the ultra-high-energy cosmic rays are nature's hidden particle accelerators, then the universe has an even more fundamental hidden architecture. We have spoken of dark matter as an invisible halo around galaxies, but what if entire galaxies could be made of nothing else? This is the startling hypothesis of the dark galaxy, a cosmic ghost made of shadow. The evidence comes not from light, but from its warping effect on reality itself. When astronomers use telescopes like Hubble to survey vast fields of distant galaxies, they occasionally see something strange. The images of thousands of faint background galaxies are not just randomly oriented. In certain patches of sky, their shapes appear subtly, coherently distorted, as if seen through the rippled glass of a cosmic window. This is the phenomenon of weak gravitational lensing. The mass of any object, visible or not, warps the fabric of spacetime. When light from a distant galaxy travels through this warped region, its path bends, distorting its image. By meticulously measuring the tiny, systematic alignments of thousands of these background galaxies, scientists can map the distribution of mass in the foreground, creating a gravitational blueprint. In a few cases, this blueprint reveals a massive clump of gravity where there is absolutely nothing to see. No stars, no glowing gas, no infrared warmth. Just a concentrated knot of invisible mass bending the light from behind it. This is the signature of a potential dark galaxy, a vast cloud of dark matter that never managed to spark with the star formation that lights up a normal galaxy. One of the most famous real-world counterparts to this idea is not a pure dark galaxy, but a galaxy that comes shockingly close. Dragonfly 44, discovered in the constellation Coma Berenices, is an ultra-diffuse galaxy, a faint smudge of light. But its motions tell a different story. The few stars it does have are whizzing around at tremendous speeds, indicating the galaxy is held together by a gravitational grip thousands of times stronger than the visible stars can provide. Over 99% of its mass is dark matter. It is a galaxy in which the invisible skeleton is not just the support, it is virtually the entire body, wearing only the faintest skin of stars. The challenge with a true dark galaxy candidate is profound. How do you confirm the existence of something defined by its absence? Astronomers must rule out every other possibility. Could the lensing be caused by a cluster of faint stars or a distant, massive galaxy cluster just off the line of sight? Could it be a statistical fluke in the complex lensing map? Confirmation requires a convergence of evidence from multiple techniques, perhaps even detecting the faint radio whisper of hydrogen gas that might linger in such a structure, pulled in by the dark matter's gravity but never ignited. If they do exist, dark galaxies would be more than just cosmic curiosities. They could be the universe's foundational building blocks, the pure dark matter halos predicted by theory from which luminous galaxies later grew. They would be the hidden nodes in the cosmic web, the invisible scaffolding upon which the glittering cities of stars are built. Finding one would be like discovering the blueprint for the cosmos, written in the language of gravity alone, a silent monument to the dark architecture of all we see. That invisible architecture of dark galaxies poses a profound question. If dark matter is everywhere, why can't we see its direct signature? Perhaps we already have. At the very heart of our own galaxy, a persistent and puzzling glow suggests we might be staring right at it. The galactic center excess is a ghost in the gamma-ray machine, a diffuse haze of high-energy light that should not be there. When scientists created incredibly detailed maps using the Fermi Large Area Telescope, they faced a monumental task of cosmic subtraction. They had to account for every known source of gamma rays in the bustling galactic center, the furious emissions from supernova remnants, the lighthouse-like beams from spinning pulsars, and the diffuse background from cosmic rays slamming into interstellar gas. They painstakingly removed all these expected signals from the map. What remained was a smooth, symmetrical, and utterly unexpected excess of gamma-ray radiation ballooning out from the galactic core. This wasn't a collection of sharp points, it was a soft, roundish glow like a cosmic lantern shrouded in fog. The distribution and energy of this light became an instant clue. It matched a tantalizing prediction from particle physics. One of the leading candidates for dark matter is a theoretical particle called a weakly interacting massive particle, or WIMP. If these particles exist, they could be their own antimatter counterparts. When two WIMP collide in the dense heart of the galaxy, they would annihilate each other in a flash of energy, producing a cascade of particles that ultimately decay into gamma rays. The predicted signature of this annihilation, a smooth, spherical glow centered on the galaxy's core with a very specific energy spectrum. The galactic center excess fits that description almost perfectly. It is the closest thing we have to a potential dark matter signal in the data, but in science almost is a canyon, not a crack. The controversy erupted immediately. Could there be a more mundane explanation? The leading alternative points to a hidden population of ancient stellar corpses, thousands of millisecond pulsars, the rapidly spinning remnants of dead stars, could be littering the galactic center. Each one is too faint to see individually at such a distance, but their combined gamma-ray glow could mimic a smooth, extended excess. It's the difference between seeing a single distant light bulb and seeing the combined glow of an entire city from miles away. The individual sources blur into a haze. Other researchers have proposed unusual distributions of molecular gas or novel cosmic ray interactions. The debate is a frontline battle in astrophysics, fought with statistical models and ever more precise data cuts. Each new analysis of the Fermi data either sharpens the dark matter hypothesis or chips away at it, as teams argue over the exact shape of the excess and the completeness of their background models. This glowing mystery at the heart of the Milky Way is more than a technical dispute. It is a direct confrontation with the unknown. We are either on the verge of glimpsing the fundamental particle that shapes the cosmos, or we are discovering an entirely new, bustling population of stellar remnants hiding in plain sight. Either outcome reshapes our understanding of the galactic core, reminding us that the universe's brightest secrets are often hidden in its faintest, most persistent glows. This faint gamma-ray glow from the galactic center is a puzzle of the unseen, but a different, more tangible mystery is unfolding in the frozen archives of our own solar system. Far beyond Neptune, in the perpetual twilight of the Kuiper Belt, astronomers are tracking the paths of small, icy worlds known as trans-Neptunian objects. Their orbits are the data trails left by gravity's hand, and when scientists began to map them in detail, a bizarre pattern emerged. It wasn't random. The most distant of these objects, those with orbits taking them hundreds of astronomical units from the Sun, seemed to be herded. Their elongated paths were oddly aligned, their points of closest approach to the Sun, their perihelia, clustered in the same region of space. Even their orbital planes were tilted in concert, leaning away from the solar system's main disk. The statistical chance of this clustering happening by random orbital dynamics is vanishingly small, less than 1 in 15,000. It is as if these distant icebergs are all drifting with a hidden current. The most dramatic explanation proposed to explain this celestial choreography is a hidden conductor, a hypothetical planet 9. This would not be a small, rocky world, but a potential super-Earth or mini-Neptune, with a mass perhaps 5 to 10 times that of our own planet, orbiting hundreds of times farther from the Sun than Earth does. Its immense gravitational influence over millions of years could have sculpted the orbits of these distant objects. Think of it like a massive planet slowly swinging a lasso of gravity, gradually shepherding the orbits of smaller bodies into a clustered, aligned configuration. The predicted orbit of this unseen world would be highly elliptical, taking perhaps 20,000 years to complete a single, lonely journey around the Sun. This hypothesis is not wild speculation. It is a direct, testable prediction born from the orbital data itself. The peculiar clustering is the clue, and Planet 9 is the prime suspect. Yet, as with any good detective story, there are other leads. Could the collective gravity of the Kuiper Belt's countless smaller, unseen bodies be enough to produce this effect over billions of years? Some simulations suggest it might be possible, though the required mass is substantial. Another critical question is observational bias. Are we only seeing these clustered objects because our surveys have looked in certain parts of the sky? If future surveys find a host of similar objects with orbits pointing in all directions, the clustering would vanish, revealed as a trick of our limited perspective. This makes every new discovery in the outer solar system a crucial piece of evidence. Each faint, slow-moving dot of light tracked across the sky adds another point to the map, either strengthening the alignment or beginning to scatter it. The hunt for Planet 9, or the proof against it, is a monumental task of patience and precision, requiring us to scan the deepest, darkest reaches of our own celestial neighborhood for a world that may or may not be there. This is astronomy as forensic science, where the crime scene is the solar system, the evidence is written in orbital paths, and the verdict on a new planet still hangs in the balance. The search for hidden worlds in our solar system's dark frontier is matched by a hunt for lost oceans on our neighboring planet. Orbiting Mars, the Mars Reconnaissance Orbiter and other spacecraft have built a detailed geophysical map of its ancient scars, and one crater tells a particularly compelling story. Lomonosov Crater, a vast, shallow basin near the Martian North Pole, is not just another dent in the rust-colored landscape. Its shape, as revealed by precise laser altimetry, is unusually flat and smooth, with a distinct raised rim that seems too modest for a crater of its size. When scientists combined this topography with subtle variations in the planet's gravitational field, a fascinating picture emerged. The data suggests the impact that formed Lomonosov did not strike solid ground but a shallow body of water. The physics is akin to dropping a stone into mud versus dropping it into a pond. An impact into a sea or a saturated, water-logged crust would create a different kind of crater, one with a broad, flat floor and a less pronounced central peak, exactly the profile Lomonosov presents. This makes it a prime candidate for the smoking gun of an ancient Martian ocean, a colossal splash frozen in time. The debate, however, is far from settled. Critics point out that impact mechanics are incredibly complex, and other processes, like the later infill of the crater by lava flows or sediments, could mimic the signature of a water impact. Furthermore, the crater's age is uncertain. Did it form during the hypothesized ocean's existence or long after it had vanished? Unraveling this requires peeling back the layers of time, searching for mineralogical clues in the crater's walls that might betray the presence of ancient aqueous minerals. The ongoing analysis of this single crater is a masterclass in planetary forensics. Every pixel of spectral data, every nuance in the gravity map is a clue in a billion-year-old mystery. Is Lomonosov the indelible footprint of a vanished sea, the place where a cosmic impact sent tsunamis across a now-desert world? Or is it simply a testament to the bewildering variety of impact geology? The answer lies buried in the data, a digital echo of a time when Mars may have been a blue world, not a red one. Mars may have lost its ancient ocean, but far beyond our solar system, other worlds are hiding their true faces behind veils of another kind. The Kepler Space Telescope revolutionized our understanding of planets by watching for the tiny, periodic dips in starlight caused when an alien world transits or passes in front of its host star. These transit light curves gave us a planet's size and orbital period, revealing thousands of new worlds. Yet for a puzzling subset of these discoveries, the initial data was just the beginning of the mystery. Follow-up observations with the Hubble Space Telescope deepened the enigma. Astronomers used a technique called transmission spectroscopy, studying the starlight that filters through a planet's atmosphere during a transit. Different gases absorb specific colors of light, leaving fingerprints in the spectrum. For many exoplanets, this reveals the chemical makeup of alien skies, showing water vapor, methane, or sodium. But for others, the data returned a baffling result, a flat line. The spectrum showed no dips, no absorption features at all. It was as if the atmosphere was completely blank, a smooth, opaque screen. The archetype of this mystery is a world called GJ1214b, a planet slightly larger than Earth orbiting a red dwarf star. Its density, derived from its mass and size, is surprisingly low. It is puffy like a cosmic cotton ball, and its transmission spectrum is famously featureless. So what is hiding the chemical signatures of its air? The leading explanations paint two radically different portraits of this world. One possibility is a water world with a steamy atmosphere. Imagine a planet with a rocky core utterly drowned under a globe-spanning deep ocean hundreds of miles thick. The heat from its star would boil the upper layers into a thick, uniform shroud of steam and high-altitude clouds. This dense, watery haze could effectively block our view of any deeper atmospheric layers, creating that flat, blank spectrum. The other leading theory suggests a mini Neptune with a primordial hydrogen envelope. This planet would have a small rocky core surrounded by an immense, deep atmosphere of lightweight hydrogen and helium, the original gases from the star's birth cloud. High up in this atmosphere, photochemical reactions could create a global layer of opaque haze, a smog of complex hydrocarbons that acts like a planetary scale veil, preventing us from seeing the chemistry below. Both scenarios are plausible, and both are profoundly alien to our Earth-based experience. The flat spectral line is not an absence of data, it is a data point of profound obscurity. It tells us that something is actively hiding the planet's nature, whether a global ocean steam or a primordial atmosphere's haze. These empty Kepler planets challenge our categories. They are worlds defined by what we cannot see, their true identities locked away behind a literal atmospheric curtain, reminding us that the universe specializes not just in revealing wonders, but in crafting perfect disguises. The blank spectra of distant worlds hide their atmospheres, but a far grander form of obscurity governs the fate of the cosmos itself. Our understanding of this fate hinges on a very specific kind of stellar explosion, a cosmic bomb so reliable it acts as a measuring tape for the universe. These are Type Ia supernova, the thermonuclear detonations of white dwarf stars. When a white dwarf, the dense cinder of a sun-like star, steals too much matter from a companion, it crosses a critical threshold. The resulting runaway fusion reaction tears the star apart in a flash of light so brilliant it can outshine an entire galaxy. Crucially, the physics of this detonation is so uniform that every type Ia supernova reaches nearly the same peak intrinsic brightness. They are nature's perfect standard candles. By measuring how bright they appear to us, their apparent brightness, astronomers can calculate their true distance with remarkable precision. It is like seeing identical light bulbs strung out across a dark plane. The fainter ones must be farther away. In the late 1990s, two independent teams used this cosmic ruler to map the expansion history of the universe. They expected to find that the gravitational pull of all matter was gradually slowing the expansion from the Big Bang. The data delivered a shock that would win them the Nobel Prize. The distant supernovae were fainter than expected. They were farther away than the models predicted. This could mean only one thing: the expansion of the universe was not slowing down. It was speeding up. Some mysterious repulsive force counteracting gravity was pushing galaxies apart at an ever-increasing rate. This force was named dark energy. The simplest explanation, encoded in Einstein's equations as the cosmological constant, describes dark energy as a constant property of empty space itself, a steady pressure that never changes. Its strength is represented by a parameter scientists call W, which is set to -1 in this simple model. Now, decades later, powerful new surveys like the Dark Energy Survey have observed thousands more of these supernovae with exquisite precision. As they refine the cosmic ledger, a subtle but persistent tension has emerged in the data. The measured value of W, the strength of dark energy, might not be exactly -1. The numbers hint that it could be slightly different. This tiny deviation is the whisper of a potential revolution. If W is not constant, it means dark energy is not a static feature of the vacuum. It could be evolving, changing in strength over the vast span of cosmic time. Perhaps it is a dynamic field, like the one thought to have powered the universe's explosive birth in inflation, but now acting as a gentle, growing push. Or perhaps our understanding of gravity itself needs revision on the largest scales. This anomaly sits at the precipice of our knowledge. It is a discrepancy measured in decimal points, a faint tremor in the data that could signal the collapse of our simplest, most elegant model for cosmic destiny. Is dark energy truly the immutable cosmological constant, or is it something stranger, something that changes as the universe ages? The answer will tell us whether the cosmos will expand forever into a cold, lonely silence, or if this accelerating flight could one day twist into something even more unexpected, a future written in the fading light of exploded stars. The accelerating universe is charted by exploding stars, but its most elusive messengers are not made of light. They are the universe's ultimate ghosts, particles so indifferent to matter they can pass through a light year of lead without a single interaction. These are neutrinos, and for over a century they arrived at Earth from the cosmos with no identifiable home. That changed on September 22, 2017. Deep in the Antarctic ice, a single, impossibly energetic neutrino struck an atom. It carried a staggering 290 tera-electronvolts of energy, millions of times more powerful than those from our Sun. This event alone in the Ice Cube Neutrino Observatory's vast detector grid was remarkable, but what happened next rewrote astronomy. An automated alert shot out to observatories across the globe and in space. Within moments, telescopes swiveled to look. The Fermi Gamma-Ray Space Telescope had data from that same patch of sky. It showed a blazar, a monster known as TXS 0506+056, was in a state of violent eruption. A blazar is the heart of an active galaxy, where a supermassive black hole feasts on matter and blasts out twin jets of plasma and radiation at nearly the speed of light. One jet is pointed almost directly at Earth, making it appear ferociously bright. The correlation was undeniable. For the first time in history, a high-energy neutrino, a ghostly particle with mass, had been traced back to a specific source in the cosmos. This was the dawn of true multi-messenger astronomy, where we no longer just see the universe but feel it through different fundamental signals. The mystery lies in the brutal physics of that distant jet. To produce such a high-energy neutrino, protons must be accelerated to near light speed within the magnetic maelstrom and then collide with other particles. These collisions create pions, which then decay into both gamma rays and neutrinos. Detecting both from the same source is the smoking gun for this process. Yet the data presents a puzzle. The models suggest the jet should have produced many more neutrinos than IceCube detected alongside the gamma-ray flare. It is as if we heard a single, deafening gunshot from a machine gun we saw firing a sustained burst. This discrepancy forces a profound question. Are our models of particle acceleration in these relativistic jets incomplete? Could the environment be far more complex, with dense clouds of gas or radiation fields inside the jet that absorb particles or alter their output? Or does this single neutrino event represent a rare, catastrophic collision within the jet, a one-in-a-billion interaction that we were miraculously positioned to catch? The identification of TXS 0506 plus 056 was not an end but a beginning. It proved that the universe's most powerful particle accelerators are not just brilliant beacons of light, but also factories for intangible ghosts. It gave us a new sense to perceive the cosmos, one that feels the shudder of distant cataclysms through particles that whisper secrets light alone can never tell. That ghostly neutrino was a messenger from a mature cosmic monster, but the universe also writes its creation myths in the flickering light of its newborn stars. Buried in the torrent of data from the Kepler Space Telescope's K2 mission is a gallery of bizarre light curves from young stellar objects, stars still swaddled in the dusty cocoons of their birth. These are not the clean, periodic dips of an orbiting planet. They are chaotic, dramatic, and deeply strange. A star known as Epoch 204278916, for instance, did something astonishing. Over the course of a single day, its light plummeted by a staggering 65%. Imagine our own sun suddenly dimming to just a third of its normal brightness, not for an eclipse, but because something vast and shapeless drifted by. The light curve from that event is a jagged cliff. The star's brightness dropped sharply, lingered in the deep shadow, and then recovered just as abruptly. Other young stars showed different patterns, slow, rolling declines that last for weeks, or a series of erratic, asymmetric dips that look nothing like the tidy signature of a spherical world. This is the messy, violent data of solar systems being born. The leading explanation points to the primordial chaos of the protoplanetary disk, the swirling pancake of gas and dust from which planets coalesce. What we could be witnessing are swarms of giant comets, hundreds of times larger than Halley's Comet, passing in front of the star in a disordered parade. Their dusty tails, stretched across millions of miles, would blot out starlight in irregular ways. Alternatively, we might be seeing the shadows cast by colossal clumps of planet-building material, dusty planetesimals on eccentric orbits, or even vast, warped structures within the disk itself. Some of these young stars bear an eerie resemblance to the more famous Tabby star, whose deep dimming sparked theories of alien megastructures. The similarity suggests that the same natural processes that create extreme shadows in infant star systems might also occasionally occur or leave behind debris in more mature ones like Tabby's. These dips are not problems to be solved so much as they are raw footage of a cosmic construction site. They provide a real-time, if cryptic, window into the most important chaotic process in the universe, the violent, dusty, and profoundly creative act of building planets from stardust. The violent construction of young solar systems inevitably ejects some of its building materials, casting them adrift into the eternal dark. These cosmic orphans reveal themselves not by their own light, but by the fleeting distortions they impose on the light of others. This is the mystery of gravitational microlensing and the strange cases where the lens itself is a ghost. When a compact object, a star, a planet, or something else drifts precisely between Earth and a distant background star, a remarkable thing happens. The foreground object's gravity acts as a natural magnifying glass, bending and focusing the background star's light. From our perspective, the distant star does not just brighten smoothly. It brightens in a very specific, symmetric curve, a spike of light with a predictable shape and duration. The duration of the event tells us the mass of the lens. A star might cause a brightening that lasts for weeks. A Jupiter-sized object would cause one lasting just a day or two. It is a flawless cosmic scale. Yet, in a growing number of these events, when astronomers point their most powerful telescopes to the location of the lens after the event has faded, they find nothing. Absolutely nothing. The mass has been measured, sometimes equivalent to a planet, sometimes to a small star, but the space is empty. No glow of a star, no infrared warmth of a brown dwarf. Just the cold void. So what exactly did the light from that distant star just bend around? The most thrilling possibility is a vast population of rogue planets. These are worlds untethered from any sun, violently ejected from their home systems during the chaotic gravitational scuffles of youth. Billions, perhaps trillions of these frozen, dark nomads could be drifting through the interstellar spaces of our galaxy. A lone Earth or Neptune floating in the abyss would be far too cold and faint for our telescopes to see directly. But when it passes in front of a distant star, its gravity, however small, still warps spacetime, betraying its presence in a brief, perfect spike of light. Another, more exotic candidate is even darker. Could these invisible lenses be primordial black holes? These would not be the black holes formed from collapsing stars, but hypothetical relics from the universe's first second, when extreme densities could have squeezed matter into tiny, dense knots. A black hole, the mass of a planet or a star, with no surrounding accretion disk to glow, would be utterly black against the black of space, detectable only by its gravitational grip on light. Each unexplained microlensing event is a census of the invisible. It forces us to ask what the galaxy is truly made of. Is the space between the stars filled with a silent diaspora of lost worlds, the casualties of cosmic billiards, or are we mapping an unseen geology of spacetime itself, dotted with ancient singularities? Every time a star brightens for no apparent reason and then fades, leaving no trace, we are given a single, tantalizing day to point in the search for the galaxy's dark, wandering population. The reliability of our cosmic yardsticks is the bedrock upon which we've built our map of the universe. Yet, one of our most trusted tools, the Cepheid variable star, is beginning to show cracks in its foundation. These are not ordinary stars. Cepheids are cosmic lighthouses that pulse with a steady, predictable rhythm, growing brighter and dimmer over days or weeks. The key discovery, made over a century ago by Henrietta Swan Leavitt, was profound. The longer the pulsation period, the more intrinsically luminous the star. Measure its period from the light curve, and you know its true brightness. Compare that to how faint it appears from Earth, and you can calculate its distance with remarkable precision. This period luminosity relationship transformed Cepheids into the first rung on the cosmic distance ladder, the crucial stepping stone we use to measure the scale of other galaxies and discover the expansion of the universe itself. Now, data from the Hubble Space Telescope is revealing troubling inconsistencies. When astronomers use Cepheids to measure the distance to a galaxy, and then cross-check that distance with another independent method, like the brightness of Type I, a supernova in that same galaxy, the numbers sometimes disagree. The discrepancy is often small, a few percent here or there, but in the precise world of cosmology, that is a glaring red flag. This isn't just about one galaxy. It feeds directly into the most pressing tension in modern cosmology, known as the Hubble tension. This is the growing conflict between two methods of measuring the universe's current expansion rate. One method uses the cosmic microwave background, the ancient afterglow of the Big Bang. The other uses Cepheid-calibrated supernova in the relatively nearby universe. These two methods, one looking at the infant cosmos and one at the modern cosmos, are yielding stubbornly different answers for how fast the universe is expanding today. The Cepheid anomalies suggest the problem might lie in our local measurements. Could our fundamental rulers be flawed? The suspicion falls on the Cepheids themselves. Perhaps their period-luminosity relationship is not as universal as we thought. A star's metallicity, the abundance of elements heavier than hydrogen and helium, might subtly affect its internal physics and how it pulsates. A Cepheid born in a galaxy with different chemical enrichment could be slightly brighter or dimmer than our standard formula predicts. Even more insidiously, interstellar dust could be the culprit. Dust scatters and reddens starlight, making a star appear fainter and farther away than it truly is. If the dust in a particular galaxy lane is clumpier or of a different composition than we've accounted for in our models, it could throw off the Cepheid distance and, by extension, the calibration of every supernova in that galaxy. Every anomalous data point from a pulsing star forces a profound recalibration. If we cannot absolutely trust the Cepheid, the entire distance ladder above it begins to wobble, and with it our precise understanding of the universe's size, age, and ultimate fate. The search is now on for a hidden variable, a subtle property of these stellar metronomes that we have overlooked because the stability of our cosmic map depends on it. While Cepheid stars form the shaky rungs of our cosmic distance ladder, a brand new class of object has appeared in a different spectrum of light, one so strange it had no name until we saw it. They are the odd radio circles, and they are exactly what their name suggests. In 2019, astronomers processing the first wide-field survey data from a revolutionary new instrument, the Australian Square Kilometre Array Pathfinder, or ASCAP, spotted something that made no sense. Scattered across the radio sky were faint, perfect circles. They were not centered on any known galaxy, quasar, or star. They were just there, immense ghostly rings, visible only in the specific radio wavelengths that ASCAP was built to capture. When scientists pointed other telescopes, optical, infrared, even X-ray, at those exact coordinates, they saw nothing at all. The circles were radio ghosts. The scale of these structures is almost incomprehensible. A single odd radio circle can span hundreds of kiloparsecs. To put that in human terms, 1 kiloparsec is about 3,260 light-years. Our entire Milky Way galaxy is roughly 30 kiloparsecs across. One of these faint rings could easily enclose 10 Milky Way galaxies side by side within its circumference. They are not small smudges, they are titanic halos etched onto the canvas of deep space, and we have no idea what is drawing them. The immediate question is, what cosmic event could produce a perfectly spherical shockwave on such a staggering scale? One leading theory points to the most violent marriage in the universe. When two galaxies collide, their central supermassive black holes eventually spiral together and merge, releasing a tsunami of gravitational waves. That merger might also unleash a cataclysmic spherical burst of energy. The resulting shockwave, expanding for hundreds of millions of years, could illuminate the intergalactic medium in radio waves, leaving behind one of these perfect circles as its only fossil. Another idea suggests these could be the throats of distant wormholes, or perhaps a new, unprecedented type of nebula surrounding an entire galaxy cluster, illuminated by some unknown process. What makes the odd radio circles so profoundly exciting is not any single theory, but their very existence. They were not predicted. They were not hiding in older data. They appeared only when we built a telescope with a new kind of vision, ASCAP, wide field of view and sensitivity to faint, diffuse emission. These circles are a pure discovery, a reminder that our maps of the cosmos are still incomplete. Every new instrument we point at the sky is not just answering old questions, it is revealing entirely new chapters in the universe's story, written in a light we are only just learning to see. That ghostly neutrino from a distant blazar proved we can feel cosmic violence, but sometimes the absence of a signal is just as deafening. Near the constellation Gemini, a cosmic lighthouse has been beaming for millennia. This is the Geminga pulsar, the corpse of a massive star that exploded over 300,000 years ago. It is one of the brightest sources of gamma rays in our sky, and crucially, it is close, a mere 800 light-years away. For scientists studying the sea of high-energy particles that washes through our galaxy, Geminga is a perfect laboratory. It is a known, nearby engine for cosmic rays, the protons and atomic nuclei accelerated to near light speed. But when researchers pointed the Fermi Large Area Telescope at the region around Geminga, the data revealed a puzzling silence. They were searching for a specific signature, positrons. These are the antimatter twins of electrons, and they should be streaming from Geminga in abundance. The physics is elegant. Cosmic rays accelerated by the pulsar's powerful magnetic fields slam into the thin gas of the interstellar medium around it. These collisions produce pions which then decay, creating a predictable shower of both gamma rays and positrons. The gamma rays we see clearly, painting Geminga as a brilliant pinprick. The positrons, however, are another story. These charged particles do not travel in straight lines. They get tangled in the galaxy's magnetic fields, bouncing and scattering their way through space in a process called diffusion. Models predict that given Geminga's proximity and power, a significant flux of these positrons should have diffused their way to Earth by now, adding a measurable spike to the antimatter particles we detect in our instruments. The data shows no such spike. It is the Geminga anomaly, a bright, nearby cosmic ray factory that appears to be producing far fewer positron travelers than our best theories allow. This missing antimatter forces a profound rethink. Perhaps the diffusion of cosmic rays in our local interstellar neighborhood is far slower and more complex than we assumed. Imagine a dense fog surrounding Geminga, a region of tangled magnetic fields that traps the positrons close to home, preventing them from escaping into the wider galactic currents that would eventually bring them to our doorstep. Or maybe our understanding of the acceleration and collision processes at the pulsar itself is flawed. Could Geminga be producing cosmic rays in a different way or with a different composition than our standard models predict? This quiet deficit in the data is a whisper about the fundamental conditions of our local galactic environment. It tells us that the space between nearby stars is not a uniform highway for high-energy particles, but a landscape with unseen barriers and slow zones. Solving the Geminga anomaly means mapping the invisible topography of the magnetic fields we float within, and learning why one of our closest stellar neighbors keeps its antimatter secret so closely guarded. Our most precise cosmic recipe is missing a key ingredient. In the furious first minutes after the Big Bang, the universe was a seething nuclear furnace. This period, known as Big Bang nucleosynthesis, forged the universe's first atomic nuclei from a primordial soup of protons and neutrons. The calculations are breathtakingly precise. Given the known density of the universe and the laws of nuclear physics, the standard model predicts exactly how much of each light element should have been created, about 75% hydrogen, 25% helium, and trace amounts of deuterium, helium-3, and lithium-7. For hydrogen, helium, and deuterium, the predictions match the observed abundances in the oldest stars and pristine gas clouds almost perfectly. It is a triumph of cosmology. But for lithium-7, the numbers are catastrophically wrong. The oldest, most metal-poor stars in our galaxy, which act as cosmic time capsules preserving the chemical makeup of the early universe, show only about 1/3 of the predicted amount of lithium. This is the cosmological lithium problem. It is not a small rounding error. It is a factor of 3 discrepancy that has persisted for decades, a glaring mismatch between our elegant theory of creation and the hard data written in starlight. So where did all the lithium go? One line of investigation looks to the stars themselves. Could these ancient stars have somehow destroyed their primordial lithium over billions of years? As a star ages, lithium is fragile. It burns at relatively low temperatures in a stellar interior. Perhaps these old stars have deeper convective zones that dragged surface lithium down into their hot cores, where it was fused into other elements. Or maybe the surfaces of these stars were polluted by accretion of lithium-poor material, diluting the original signature. Yet, detailed models of stellar evolution struggle to account for the uniform factor of 3 depletion seen across so many different stars. The other, more radical possibility is that our understanding of the universe's first minutes is incomplete. Could there have been unknown particles or forces at play during Big Bang nucleosynthesis that altered the nuclear reaction chains? Perhaps exotic particles like decaying gravitinos or other supersymmetric partners injected extra energy, changing the delicate balance of reactions that built lithium. Some theories even suggest that patches of the early universe had different densities, leading to inhomogeneous nucleosynthesis that produced less lithium on average. Each proposed solution faces intense scrutiny because tampering with Big Bang nucleosynthesis to fix the lithium problem risks throwing off the perfect agreement we have for hydrogen and helium. It is a high-stakes puzzle. The lithium problem is a quiet but profound crack in the foundation of our origin story. It tells us that for all the majestic success of the Big Bang model, a piece of the narrative from its very first chapter is still missing, waiting to be found in the faint light of the oldest stars. Mercury's scorching orbit holds a secret of emptiness. For more than a century, astronomers believed a hidden family of asteroids named volcanoids must be circling the Sun inside the path of the innermost planet. The original motivation was a genuine puzzle in Newtonian gravity. The slow, steady rotation of Mercury's elliptical orbit, its perihelion precession, which could not be fully explained by the gravitational pull of the other known planets. The logical solution seemed to be an unseen mass, a swarm of small worlds orbiting closer to the Sun, tugging on Mercury and warping its path. It was a clean, elegant fix, and the hunt for Vulcan began. When Albert Einstein's theory of general relativity perfectly explained the precession without any extra matter, the theoretical need for the asteroids vanished. Yet the practical question remained: even if they weren't needed to explain Mercury, shouldn't such a region of space so close to the Sun be littered with the leftover rubble of the solar system's formation? The modern hunt turned from theoretical necessity to pure exploration, using tools never designed to look into the Sun's glare. Spacecraft like the Solar and Heliospheric Observatory (SOHO) and the Solar Terrestrial Relations Observatory (STEREO) carry instruments called coronagraphs. These are ingenious devices that create an artificial eclipse inside the telescope, blocking the overwhelming light of the Sun's disk to reveal its faint outer atmosphere, the corona. This same technology also provides the only clear view into the deep sky near the Sun, the perfect vantage to spot the reflected glint of any asteroid. For decades, these observatories have patiently scanned the forbidden zone inside Mercury's orbit. The data they have returned is definitive and profoundly silent. No volcanoids have been found. This is not a case of missing a few small rocks. The null result is a measurement of stunning precision. It tells us there are essentially no asteroids larger than about 6 kilometers in diameter orbiting in that torrid region. Any population of smaller objects would have to be incredibly sparse, a ghost town compared to the bustling asteroid belt between Mars and Jupiter. This emptiness is the real mystery. Why is this zone so clean? The environment is brutal, of course, bathed in intense solar radiation and subject to extreme gravitational tides from the Sun itself. These forces could grind small bodies to dust or hurl them into the sun over billions of years. But the complete lack of even moderate-sized survivors suggests this cleansing was total and ancient, perhaps a relic of the solar system's most violent early era when the orbits of the inner planets themselves were still settling into place. The search for volcanoids, therefore, ended not with a discovery but with a profound piece of knowledge. Sometimes the most important data is what you do not see. The blank images from the solar coronagraphs have drawn a map of a forbidden desert, a region of our own solar system that remains strangely and beautifully void. That map of Mercury's forbidden desert was drawn in visible light, but our galaxy holds a different kind of map, one written in the quiet hum of microwaves. As satellites like Planck and Oumuamua meticulously scanned the heavens, they were building a cosmic inventory, cataloging every source of microwave radiation to understand the universe's structure. Most of the signal fit into neat categories: the sharp hiss of synchrotron radiation from electrons spiraling in magnetic fields, the soft crackle of free emission from hot gas, and the steady warmth of thermal radiation from interstellar dust. But when all these known sources were subtracted from the data, a ghost remained. A faint, diffuse, and pervasive glow lingered in the microwave maps, clinging to the silhouettes of interstellar dust clouds like a strange aura. It did not match the spectral signature of any known process. This was the anomalous microwave emission, or ME, a whisper in the data that had no name until it was heard. The key to the mystery lay in its unique fingerprint. When scientists broke this faint glow down into its constituent wavelengths, they found its intensity peaked sharply at a frequency around 30 GHz, which corresponds to a wavelength of about 1 centimeter. This was the critical clue. Synchrotron radiation is brightest at lower frequencies and fades away at higher ones. Thermal dust emission does the opposite, becoming brighter at much higher frequencies. The anomalous microwave emission sat in a perfect, unexplained sweet spot between them, a bump in the spectrum that refused to fit the established models. It was as if the dust clouds themselves were humming on a very specific, unknown note. The hunt for the source led physicists from the vastness of space to the precision of the laboratory. The leading theory that emerged is as elegant as it is strange. Imagine the interstellar dust we often picture as microscopic specks of soot or sand. Now imagine that some of those specks are not just tumbling but spinning furiously, billions of times per second. These would be nanoparticles, perhaps large molecules like polycyclic aromatic hydrocarbons, those flat sheets of carbon rings, or tiny flecks of silicate minerals. If these particles carry a slight electric charge imbalance, an electric dipole, then their insane rotation becomes a microscopic radio transmitter. A spinning dipole emits radiation, and for a nanoparticle spinning at billions of revolutions per second, the radiation it emits falls precisely in the microwave band, right where the anomalous emission was detected. This mechanism was dubbed spinning dust. Laboratory experiments and sophisticated quantum mechanical calculations have shown that this idea is not just plausible, it fits the observed spectral peak remarkably well. The data suggests these nanoparticles are not floating freely in empty space, but are embedded in the denser, colder clumps of molecular clouds. There, occasional collisions with hydrogen atoms can set them spinning at just the right dizzying speeds to produce the observed microwave hum. It is a form of celestial mechanics operating on a scale almost too small to fathom, where the jostle of atoms translates into a detectable cosmic signal. Solving the mystery of the anomalous microwave emission does more than just fill in a blank on an astrophysical checklist. It reveals a hidden component of the interstellar medium. For decades, we knew dust existed, but we thought of it in broad categories of big grains, small grains. The ME data suggests there is a vast, hidden population of the very smallest grains, a nanoscale component to the cosmic dust that fills our galaxy. Understanding this population is crucial because these nanoparticles are likely the basic building blocks of larger dust grains, and they play a fundamental role in the chemistry of space, shielding molecules, catalyzing reactions, and possibly even carrying the raw materials for life between the stars. That faint, anomalous glow is therefore a direct signal from the universe's smallest architects, a microwave whisper telling us that the grand tapestry of the cosmos is woven in part from spinning specks of dust. The universe's smallest spinning dust is a whisper compared to the solar hurricane screaming past humanity's newest explorer. NASA Parker Solar Probe is a mission of unprecedented daring, a spacecraft built to dive into the Sun's outer atmosphere, the corona, and survive. As it completes each blistering orbit, dipping closer than any human-made object has ever been, its instruments are not just collecting data, they are rewriting the textbook on our home star in real time. The probe's initial data streams back a portrait of a realm far more dynamic and violent than our best models predicted. At the heart of this revelation is a phenomenon so strange it needed a new name: magnetic switchbacks. These are not subtle fluctuations. A switchback is a sudden, dramatic reversal in the Sun's magnetic field, a kink in the fabric of space itself that travels outward with the solar wind. Imagine sailing on a river where the current is flowing steadily in one direction, and then, without warning, you hit a patch where the water whips around and flows backward just as powerfully before snapping back to the original flow. That is what the Parker Solar Probe is flying through. Its in situ magnetometers, measuring the magnetic field right at the spacecraft, record these events as jagged, S-shaped lines in the data, a complete 180-degree flip that lasts for seconds or even minutes before snapping back. The sheer prevalence of these structures was the first major shock. They are not rare curiosities, they are a fundamental feature of the young solar wind, appearing with startling frequency as the probe ventures closer to the Sun. So what is cracking the Sun's magnetic whip? The leading theory points to a process called magnetic reconnection on the solar surface. The Sun's surface is a tapestry of magnetic loops and arcs, constantly tangling and straining. When these stressed field lines break and reconnect in a new configuration, they release colossal amounts of energy, like a rubber band snapping, and can fling out parcels of plasma and twisted magnetic field. These ejected bubbles of tangled magnetism could be the switchbacks the probe encounters. Another idea suggests they are generated by turbulence in the solar wind itself, as different streams of charged particles shear past one another, folding the magnetic field into these sudden reversals. Each new perihelion pass, each closer dive into the inferno, provides a clearer test of these ideas. The probe's particle detectors measure the ions and electrons caught in these events, revealing how the switchbacks accelerate particles and heat the solar wind, solving a long-standing mystery of why the corona is millions of degrees hotter than the Sun's visible surface. Every dataset beamed back from that sunward plunge holds the potential for another fundamental surprise. The Parker Solar Probe is doing more than just observing. It is touching the star's atmosphere, gathering forensic evidence from the scene of a perpetual storm. Its journey shows that even the most familiar celestial body, the star that gives us light and life, is a frontier of unexplained phenomena, its simplest winds laced with structures we are only beginning to comprehend. Mapping the shape of our own home from the inside is a cosmic challenge of perspective. We are like ants trying to sketch the blueprint of a cathedral while crawling across its floor. For our Milky Way, one of the most fundamental features we've identified is its central bar, a dense, elongated structure of stars and gas at the galactic core, thought to drive the spiral arms. Yet, when we try to pin down its exact dimensions, the data begins to argue with itself. This is the galactic bar paradox. One method relies on simple star counts. Space telescopes like Spitzer, which peered through dust in infrared light, gave us stunning images of the central bulge. By mapping where the density of stars peaks and falls away, astronomers could trace the bar's outline, estimating its length at something like 10 to 15,000 light-years. It seemed like a solid measurement, a snapshot of structure, but then came the data from motion. The European Space Agency's Gaia mission is performing a monumental census, precisely tracking the positions and velocities of over 1 billion stars. By analyzing the complex dance of stars in the galactic center, scientists can use stellar kinematics to weigh the bar's gravitational influence and deduce its properties. This dynamical picture sometimes tells a different story. The bar's rotation speed, its exact orientation relative to the Sun, even its length, these kinematic estimates can diverge from the static picture painted by star counts. Add a third method, studying the flow of interstellar gas clouds as they orbit the core, and you get yet another perspective, another potential set of numbers. So why the disagreement? The answer lies in the bar's nature and our limited vantage point. This is not a rigid, solid structure like a metal rod. It is a dynamic, evolving swarm of hundreds of millions of stars, all moving on their own orbits within the bar's overall gravitational potential. Some stars are just passing through, while others are permanently trapped in its elongated paths. Different observational techniques are essentially sampling different subsets of this population. The infrared surveys might be dominated by older, redder giants that trace one density profile. Gaia's precise motions might be best for younger, faster stars that respond to the gravity in a slightly different way. Furthermore, we are seeing the bar at an angle, not from above. Determining its true three-dimensional shape from our position within the galactic disk is a monumental geometric puzzle, where small errors in distance measurements can lead to large errors in the inferred size. This paradox is not a failure of science, but a signature of its progress. It reveals the Milky Way's bar as a living, breathing entity, not a frozen sculpture. The conflicting data forces us to build more sophisticated models that can reconcile all these observations at once. Models where the bar might have a complex inner structure, or where its ends are frayed and diffuse. It is a humbling reminder that the greatest mysteries are not always in the distant cosmos. They can be right here in the heart of our own galaxy, where the very tools we use to see shape what we find. And so our journey through the cosmic data ends with a simple, humbling count, 35. From the solar system's silent edge to the faintest whisper of the ancient sky, each phenomenon is a testament not to what we know, but to what we do not. They are not failures of science, but its very fuel, the stubborn anomalies, the ghostly signals, and the impossible orbits that refuse to fit neatly into our models. These puzzles, written in light, gravity, and motion, are the universe's way of asking better questions. They push our instruments to new extremes and force our theories to evolve, proving that discovery is not just about finding answers, but about learning how much more there is to ask. Whether it is the dark matter hiding galaxies or the hexagon spinning at Saturn's pole, each mystery reveals a cosmos far weirder, more dynamic, and more wonderfully strange than any fiction. So as you look at the night sky, remember that the greatest stories are not yet written. They are waiting, encoded in the next burst of data, the next unexplained flicker. Which of these 35 cosmic riddles captures your imagination the most? Let us know in the comments below. If you enjoyed this deep dive into the universe's greatest secrets, please subscribe and hit the notification bell. Thank you for watching, and wherever you are, keep looking up.